Hello everyone, this is Hello everyone, this is Joshua Foreman with Physics 2211 Lab 3, the black hole experiment. So the goals is part 1, find the mass of the black hole using the computational model, which is given to us, and the Newton's law of gravitation. And part 2 is to find the initial velocity required to escape the black hole without crashing into the planet. Physics concepts we're going to need to know is Newton's gravitational formula, which is gravitational constant times the mass of the first object times the mass of the second object over their distance squared times the position vector, unit vector, pointing from one planet to the other. The gravitational constant is given below. We have F equals dp dt. P is momentum. Momentum is the same as mass times velocity, so dp dt is just ma. But what's great about using dp dt is that you can split it up into p hat times magnitude of p, and use the product rule of derivatives to separate it into the color-coded F parallel and F perpendicular shown below. And then, as always, we're going to have to use the position update and the velocity update formula, which I will show you later, and you've seen in previous videos. So the initial conditions for my code for part 1. The initial conditions for the code for part 1 is pretty simple. We have the planet's, the star's mass given, and I used a day's worth of time for delta t, just to speed it up a little bit. And, delta v equals v final minus v initial, delta p equals p final minus p initial. P equals mv. So the p initial equals star's mass times velocity initial, because a momentum is mass times velocity. So same goes with final. dp dt is the same thing as f net. So delta p over delta t is the same thing as f net, which is why we substituted that in. P hat is the same thing as p divided by its magnitude. And to take the derivative of that with respect to t, you take the difference over a small time interval and divide it by delta t. And we use the parallel and perpendicular formulas that I already showed you. And to find the mass of the black hole, right at the bottom, you take Newton's gravitational formula and you rearrange it to solve for mass. You have gmm over r squared. You solve for the first m. Code for part 2. I used the black hole's mass, finding the average of all the black hole masses because they changed a little bit. So I found the average, and I put it in for bh.m. Those are the only initial conditions here. Oh, in the bottom, these were the correct velocities, or not the correct, but a correct velocity components in order to escape the black hole, which will be shown a little bit later. So we have the position. We have the positions subtracting from each other gives you the position vector, the r from black hole to planet. It's always final minus initial. Force is g times mass over r squared times r hat. And same goes with the other two, the ship and the black hole. It uses the same math, same formulas, everything. And F net is the force from the black hole plus the force from the spaceship. That's important to know. And the notorious position and velocity update formulas, instead of using acceleration, we use F divided by m, which is the same thing as acceleration. So that's why there's F net in it. And it turns out with these velocities, it escaped. So that's great. So what does this all mean? So dp dt and F net are equivalent. However, you need to know the mass of both the planet and the black hole in order to use F net, which you don't have. You're solving for the mass. So in order to reconcile this problem, we use dp dt, which is only required to have the mass, velocity, and time, which is great. So they're not different, but they can be used differently depending on what variables you're given. Okay, thank you. Have a good day.